My name is Ciprian-Florin, and I'm going to demonstrate my solution to the problem requiring a Ur10 robot arm to catch a flying object, for example a ball, thrown into the robot workspace. The whole code has been developed in simulation under ROS Noetic in Ubuntu, with a Python script developed in regards to the ROS ecosystem and with a Sublime editor. To begin, we must first run the Ur10 Simulator, and to do that we need to navigate to the terminal, and then from there navigate to the directory of where the URSim has been installed. Once we do that, we need to run the actual simulator, and we need to use the admin rights in order to do that. And once the simulator has opened, we can close it and then run it without admin privileges. So we are now in the simulator. We can confirm everything, and since everything is fine, we can just exit, and then we can run it again without the admin privileges, the sudo at the beginning. Once this completes fully, which should be done in any moment, and we initialize the arm, as we can see here in the window, I'm going to move it here to the right side. We can go to the another terminal window, and then we can run the URRobot drivers once they have been configured with the correct IP address from the simulator. Once we reach this point, it means that the controllers have started and the robot can find both the forward and inverse kinematics depending on the positions that are sent to it. And now we can just simply run the actual ball trajectory service which has been provided to us. The service will generate both the Cartesian as well as the rotation error from our current robot pose. So in order to do that, we can use the ROS-run command. I already have it here, and we can go to the robot control simulation package and then the ball trajectory. If we run this, we can run it in two modes, and we'll go the second one, which will check for both the angle deviation and the Cartesian distance, and only once both of those are within the thresholded values given, then the ball will be considered caught. Now that I have the ball trajectory service running and the Ur10 simulator running, in order to run my code, we simply need to go to the workspace, SRC, robot control simulator, and then there's a folder called Trajectory Explorer. In here, there's another folder called Code. Here we can just open a new terminal, and once we do that, we can just do Python 3 trajectory underscore explorer, and if we run this, it will tell us that the service is starting up and that the system has started. Now when this happens, we are presented with an interface which has been developed in Tinker, and the interface presents two different modes. The first one, which is the acquire sequence mode, will try to use the algorithm that has been developed in order to get as close as possible to the ball and within the thresholded values given, which are 5 centimeters for the Cartesian distance and 5 degrees for the rotation. Once this is complete, the user is asked if they want to save the sequence, so the sequence of movements that the arm has completed, to a CSV file. If the user chooses to do so, there is a post-processing on the entire sequence so that no repeated movements happen, especially if the repeated movements are erroneous. And then, if we go on the second mode, which is execute sequence, it will simply read the CSV file that is present and will run that sequence of movements. Now, the second mode is useful if the ball is always launched from the same point at constant velocity, therefore generating the same trajectory, which is not common and is not what our trajectory service does. However, in the case of a repeated task, such as a smart factory. Another example could be a tennis ball launcher that will always launch the ball with the same acceleration towards the same point. We can have the robot arm generate automatically the best sequence, and then without any user input, we can also have it repeat that sequence as many times as needed without having to go through the entire algorithm of searching for the correct sequence. Furthermore, on this window, outside of the two switches, there is another switch here at the bottom, which is called endless mode. If we click that, it becomes green. If we click that again, it's red. Now this switch here, what it does is it switches the way that acquire sequence works. So instead of just trying to find the ball and then catch it once, if our service can generate a new trajectory as soon as the ball has been caught, by clicking this mode, it will continuously try to catch the ball, and it will continuously listen to the trajectory service. It is important to note that the current trajectory service version does not generate a continuous trajectory, and it only does it the first time. So the user would have to manually restart the service if they want to have a continuous simulation. So let's start by going into the first mode without endless. And we have our trajectory generated, and we have our robot here, as you can be seen. And zoom in a bit. And I can press that, and now I have a new window. Now this window is for the output. I have all the output happening in this window here rather than the terminal. I have moved to the home position, as it says here, moving to the home position. And now once I got the default original values, the terminal, or rather the algorithm, will continue to move in specific directions in order to find the best distance from the arm, from the ball, and in the case of the distance being incorrect after a few movements, it will then return to the previous best position. So in this case of these four positions here, the previous best was the 15 one, 0.15. So we went there, we already found the distance. Now we are going through the algorithm that tries to find the correct angle. So we are continuously moving the actuator in one direction and then the other direction, and we do this on Rx, Ry, and Rz continuously. Now we switch it to the pitch, to the roll, to the pitch again. Now once it goes below 5, it says that we exited the while loop and the ball has been caught, and then the operation is complete, and the entire process took 58 seconds. Now it is important to note that throughout these 58 seconds there's always a 2-second delay between every single MoveJ movement. So once I'm informed about this, I can just press OK, and then it tells me, do you want to save the sequence to a CSV file? Yes, I do. So then I have added edge cases. So in this case, we have an actual file already present, and it tells us, do you want to replace it? Because it already exists. If I press cancel, it will simply exit the loop and leave the file as it is, the one that I have already saved on disk. However, in this case, I want to replace it. So I'm going to press OK, and the operation has been completed. Now that we generated our CSV file, we can go navigate to it and see how it looks like. So if we go to the workspace, SRC, robot control simulation package, and then the trajectory explorer, code, sequence CSV, this is how it looks like. So it includes all the roll, yaw, and pitch movements with the appropriate angles or distance in meters, or here in degrees, and of course the axis. So this is the entire sequence that has been completed and has been saved. Now I can simply go to my code here. I can press execute sequence. The robot will return to the same home point as before. Then the output window will reappear here. It will simply tell me that I am doing a MoveJ movement with axis and the type of axis, and then the actual distance as we talked about earlier. Now, the reason for the MoveJ type of movement is because the inverse kinematics function that Ur10 uses takes into consideration the dimensions of the robot and the position of the robot. Therefore, when you send it a movement, a position that it needs to reach, it considers all of these factors so that the robot does not go through itself. Another implementation, a limit, a condition in order to make sure that the robot follows certain security protocols, is a delay for in between every single movement, so that the movement completes fully, accurately, and it reaches from point A to point B. Another limit added to the robot, while I move this output window to the side, the sequence has been completed, and it lets me know that the sequence has been completed. As I was saying, I have also went and chosen multiple home waypoints in order to find the best one for this situation, so that the robot does not go through itself in order to reach that position. Now, since we reached the end of the code, I would like to talk about OpenAI Gym and scikit-learn reinforced learning, both machine learning implementations that I have researched for implementation purposes. However, their execution was unnecessarily complex in this scenario, and in my opinion would present minimal benefits. That is the main reason on why I decided to create my own sequence algorithm that memorizes the correct values, similar to a labyrinth solving algorithm, and then checks these sequences in order to make sure that certain movements do not repeat and the robot does not get stuck, and then it saves that to the file. It is also important that that CSV file can simply be sent together with a code to anyone, and it can be run without problems. And the CSV file can also be manually edited or manually created and executed by the code, which is another bonus. Now, if we close the code here, it asks me if I want to quit. I press yes. The program has closed. Here, I can close the ball generation. I can turn off the drivers with using Ctrl+C for a keyboard interrupt, and I can also exit the graphical user interface. This marks the end of the video demonstration, and I would like to thank you for the time dedicated.